Good evening, world. Welcome to another tour around your celestial neighborhood. I'm Irene Pease, your friendly neighborhood astronomer, right out of Brooklyn, New York. Super excited to be here tonight. We're looking at large scale structure. Very refreshing. Structure and things that have, structure and order and make sense. Science. So, yeah, tonight we're going to be using the same visuals as usual. Stellarium, we'll move over to in a moment. You can check out Stellarium at stellarium.org. And in the background right now, we have Open Space. You can download that, check it out, play around with it, openspaceproject.com. So again, we're talking about large scale structure, but first we're going to get to a little bit of what's happening in the night sky. So let's pop on over to Stellarium and check out, oh look, our night sky. So here we have our glorious Brooklyn night sky, a little bit darker than really would be in Brooklyn, but we're looking at now, a little after 8. And what's up? Oh yeah, those things that I was talking about probably last week. Uranus and Mars, really close together. I went outside last night, but I was too late and the clouds had rolled in. So maybe tonight it's supposed to be clear again in Brooklyn. Something you should see even from bright city skies. So go ahead and check that out. Uranus and Mars near each other. There's also a moon up there. That's really nice. And the moon is going to be heading over towards the little group of constellations that we've been focusing on, some more of our winter constellations. So what constellation do I want to focus on this week? Well, it's not so much a constellation, it's some star clusters, but there's some really lovely star clusters in the constellation Taurus. And if you're not sure where Taurus is, there's 2 ways you can find it this week only, and again next month and the month after that. But for this week, if you look at Orion, let's turn on stick figure Orion. Just kidding, that's the label. Stick figure Orion. There's the 3 stars in that belt. A lot of folks recognize those. They're pretty distinct, show up even in bright skies, light polluted skies. You can follow the belt up towards this kind of V-shaped cluster. I get rid of some of the names there. So there's a bright star Aldebaran. It might look slightly red or orangish, probably more orange or yellowish, really. But yeah, so the belt of Orion points right up towards that. And there's a couple other stars up there that make like this little V. That's basically the face of Taurus the bull. So a little bit of imagination to see a bull there. Here's your imagination in a bottle. Click, magical imagination. And there's the face. So there's Taurus. So Aldebaran is like the eye of a bull. And he has these horns that go up to these 2 stars. We might talk more about those another time. But then past the V-shaped cluster, you can see it's really half a bull, right? So it's like the front half. So he has front legs, and then that's it. But kind of riding on the back or shoulder of the bull, there's this nice little cluster of stars, the Pleiades, or the 7 sisters, or the 7 whatevers. So there's these have been widely recognized across cultures for, throughout history. And so really beautiful, easy to see in the night sky. Again, this is another one that shows up even in light polluted skies. And this is what I want to focus on. So you know how I feel about sparkly things. So star cluster is really great. So you have the Hyades star cluster, that V-shaped bit over the face of Taurus the bull. I think we've flown through it before. We'll probably fly through it again because it's fun, just not tonight. But that's kind of a star cluster group of youngish stars relatively close to us, and then a little bit further away from us, but also relatively young stars, the Pleiades. So most people see 6 with the naked eye. If we zoom in here a bit, there's 2 features I want you to look for. And again, these are naked eye and binocular. If you have a telescope, you can also see them, but it's almost too big to really look at in a telescope. So if you don't have a telescope, great. Just look up with binoculars and or with your eyeballs. And if you look up here, it almost looks like a mini dipper. Some people call it the mini dipper. It's not the little dipper, but it's got kind of like a little handle and like the little cup. So if you see it in the sky with your eyes or with binoculars, look for the mini dipper. And then the other super fun thing that made me pick this cluster tonight is this other kind of string of stars, all kind of like the same brightness. It actually extends out a little bit beyond what this picture is showing, like another star or 2. It's what we like to call the string of pearls. So I just wanted to put the string of pearls up there in honor of our new VP and all her glorious pearls. So the Mini Dipper and the string of pearls to look for. The Mini Dipper you can see naked eye, and then the string of pearls, if you look at that with a telescope or binoculars, you can pick out the little string of stars there that make a nice little asterism within an asterism. So that's kind of what we're looking at this week. If you're not sure about where you're looking to find the Pleiades and the Hyades, I said there was another way you can find them this week. So if we fast forward a few days, 1, 2, that's a few, the moon is going to kind of pass between them. So the moon will pass between the Hyades and the Pleiades. It'll be closer, a little closer to the Pleiades. Well, maybe not so much. Tomorrow and the next night. So is that Friday, Saturday? I don't even know what day it is. I know it's not Wednesday anymore. That's all. It's not another Wednesday. So the moon's just be going right between those. And so if you look at where the moon is the next day or two, you can see that's basically where Taurus the bull is. So that's the fun thing. Check out the Hyades, check out the Pleiades, check out the string of pearls and the Pleiades. And that's what we're looking at for this week. So again, the topic for this week I'd said was large scale structure. So I'm going to do something a little bit different in the open space. We're actually going to move really far, far away. To check and see just how far out I'm going. Not too far. So usually we start at Earth, right? And then we move far, far away. But I wanted to kind of flip that this week, just, for something different. So here we are in open space. This is actually open space without any data sets turned on. So we're going to go way back and kind of trace through time. So I'll just put on the don't panic button. So way back when the when the universe was getting started, there wasn't really radiation that could propagate. It was too dense, it was too hot, and at some point the fog lifted, so to speak, and we were able to see the first bit of light. So I'm just gonna bring that up a little bit so that you can see something, a little bit of something. There's a little bit of something. Let's move, into the universe. So we're inside the universe. So the large scale structure that we see today, that's going to refer to kind of like groupings of galaxies, strings and walls and clusters and things. But I'm just going to do a little bit of storytelling because way back in the first very, very, very small, like millionth of a fraction of a second, there were quantum fluctuations. And we think that those gave rise to teeny, teeny, tiny differences in homogeneities in the universe. And so those have propagated through in different forms. First quantum fluctuations, and then because of gravity kind of dominated after a certain point, we have what we now see as large-scale structure. So the first thing I can really show you, I can talk about like, oh yeah, there were quantum fluctuations, but I can't really show you that because they're too small. And we can't see anything from that far back. So the first light that we can see wasn't until about 380,000 years after the Big Bang, after the universe really got kicking around. So that's when we had hydrogen atoms actually forming. So once you form hydrogen, then all of a sudden radiation could propagate and it could move, and move it did. And it's still propagating through the entire universe. So this is light from the very earliest part of the universe at 380,000 years after the Big Bang. And we see it in every single direction. It's what we call the cosmic microwave background. Cosmic because it's everywhere in the cosmos. Every direction we look, it's all over the place. And microwave because it's in the microwave part of the electromagnetic spectrum. So not light that's detectable with our eyes, not light that's detectable in the infrared or UV or radio or X-ray. This is a microwave. So it's between infrared and radio. So shorter wavelength than radio, longer wavelength than infrared. And yeah, basically it's very uniform. So why does it look blotchy? Well, because it's not exactly perfectly uniform. It's very, very uniform down to 10 thousandths, just kidding, about 100 thousandth, like 1 part in 100,000th. So very, very small. So the colors that you're seeing here are representing very, very tiny fluctuations. And the colors are kind of referring to different temperatures. So overall, the whole thing, if we look out now, it's cooled off since, the last couple 13 some odd billion years. It's cooled a bit. So it used to be thousands of kelvins, but now it's about 2.7, 2.71, 2.73. Yeah, 2.73 we'll go with. 2.73 kelvins, and very uniform except for these teeny tiny fluctuations. Yeah. So that's what we're seeing here. And this was kind of predicted back when people were first started talking about the Big Bang. And then it was kind of captured by Wilson Penzias by the Horn in New Jersey. It's another story about pigeon poop. But this is the actual survey of the entire sky. So it's kind of hard to see these. And you can just kind of look at these like clouds, just enjoy the view of like, oh, I see a horse. Oh, I see a dog with a head or something. So, but it's very hard to see these like in real detail. So we put this cosmic background explorer, COBE for short, up in space, and COBE looked all over the sky. This was back in 1992. So this has been a while. And this is the map it made. So it's a pretty map. So red is hotter, blue is cooler on this map. But again, we're talking about tiny fluctuations. So like 100,000ths of a degree that we're like varying. So it's not changing a whole lot. But that's COBE. So that's kind of neat. So the universe looks blotchy, right? So you say that doesn't look very uniform. It looks blotchy. Well, that was the resolution of COBE. This was the first time we tried to really get super detailed images of the cosmic microwave background. So later on, a little down the road, we came up with another one. Bonus points. Anyone can name the next the next one. So I bring that up. Ooh. All right. So here we have slightly better resolution. So COBE, again, that was like 7-degree resolution. Not awesome. But a decade later, 2 decades later, early 2000s, I think it was 2003, we sent WMAP up there. So WMAP, that was the Wilkinson Microwave Anisotropy Probe. So basically trying to get better resolution, and better resolution it got. So this is still blotchy, but again, we're kind of refining it a bit and getting a little bit more granular. This is more like a half-degree resolution of the whole sky, and seeing that it's still very uniform. So it's uniform, but it's kind of blotchy all over. But that's part of the uniformity. So it's not perfectly 2.73 degrees. 2.73 kelvins all over the place. There's tiny fluctuations, but the fluctuations are uniform. They're in every direction. So that's still really exciting for us. But we can do better. So WMAP was also out in space. I don't have pretty pictures of it here, but that's the all sky survey. And it did several different data releases. The most recent, I believe, was in 2012. That was like the 9th release. So they just kept getting like better and better. And then eventually 2013, there was a ESA mission, the Planck satellite. And so Planck, whoa, just like we went from this to this. And so that's even better resolution. This is like 15 times the resolution of COBE, the original. So this is our cosmic microwave background. This is the earliest light from the universe, and basically what's giving rise to large-scale structures. So quantum fluctuations we can't see, but these tiny differences in color in the cosmic microwave background we can see. And again, I said that the colors correspond to temperature. Red actually means hotter, blue means colder, even though in reality, if you look at like a blue stars are hotter than red stars. But anyway, it's a color scheme. So red is warmer, but only tiny, tiny bit. Blue is cooler, but only tiny, tiny, tiny bit. And those cooler regions, that's where you could have slightly denser bits of matter. So it's those cooler bits where we get a little bit more density, and the warmer bits where you get a little bit less density, and just kind of gravity takes it from there. So a few million years later, so jump forward in time, we'll say several million years, and we start getting stuff forming, like actual matter. So not just some hydrogen gas here and there, but if I go ahead and turn these down a little bit, we get to stars, galaxies. That's what we care about next. Looking at some of the galaxies. So we have several data sets, and we're starting off with Sloan. So coming in here a little bit closer. So these are more recent, so we're going to be moving actually closer and closer to the Earth as we move through here. So we started far, far away, way at the edge of the observable universe, but now we're moving in. So there's a question, comment, is this like infrared picture of the sky? So the cosmic microwave background, again, that's in the microwave part of the spectrum. So longer wavelengths than infrared, not as long as radio, but think about it as like really short radio waves. We call it microwave for the same reason that you call your microwave the microwave. So if you know the wavelength of the electromagnetic waves generated by your microwave, which you can find either by spreading chocolate chips on it and setting it and then like measuring the distance between the melted bits, or look at the frequency that should be printed somewhere on your microwave, and then divide the speed of light by the frequency, that gives you the wavelength. Yeah. So, yeah, should be a few centimeters. But then this is looking at galaxies. So every dot here now is a galaxy. So the cosmic microwave light, all that light is still propagating through the universe. It's still all around, everywhere we look. Again, it's everywhere in the universe. But now we're coming in and we're looking at closer things, so more recent things. So newer, fresher, older history of the universe, closer to our point in time. And I wanted to pop on a couple other data sets, see how many of these I can turn on before this crashes. That wasn't supposed to be quite so big. And one more data set, see if we can break this. Oh, it didn't break. Okay, so so we have lots and lots of galaxies here. So the first data set, that was basically the Sloan Digital Sky Survey of galaxies. It's 2.5 million. So with the other galaxy sets we're looking at here, a few million, 3 or 4 million galaxies. So all these dots, again, every dot is a galaxy. And what do we see? Well, okay, a bunch of dots. The colors, so the kind of oranger bits, those are indicating regions of more density, right? So we were talking about like large scale structure. So you can see maybe not all on the sides, but around in here, and maybe like over in here, kind of on either side of this bow tie butterfly kind of feature, you can see kind of like a spongy, webby texture. That is our current large scale structure. So farther away means, again, farther back in time, but if we come in here, and maybe I'll just turn off a couple data sets, it's kind of like overkill. Yeah, that's plenty. We see this kind of webby structure. So again, remember those cooler regions that we saw in our cosmic microwave background, those allowed more matter to condense. So it's like a little bit denser. So those could lead to denser regions that we see today. And then the slightly warmer spots that we saw in the cosmic microwave background, those would be slightly less dense, and those could lead to places where we see voids in the structure today. So it's this kind of webby, spongy texture with walls and filaments, and then the voids in between, and pretty exciting. So people are still like doing a lot of research connecting a lot of these dots, like literally, well, not literally these dots, but connecting the dots from trying to get to from quantum fluctuations through the cosmic microwave background and then to the structure that we see today, and seeing what's happening with that, with other exciting things that I'm not really too qualified to talk about, but like basically dark energy and like why is this tearing the universe apart and stuff. So just a couple other things I wanted to point out in here. Um, if I just kind of turn down the number of galaxies we have, I'm going to turn off the 2.5 million and just limited us to the 2DF. This is our 2-degree field of view. And just talk a little bit about like why we're seeing what we're seeing here. So if we look at it like from this angle, it's very butterfly-like. If we rotate it around, you can see it's kind of slices. So these are slices of degrees of the sky. So basically a 2-degree field of view as seen from Earth, but then spreading out away from Earth, that's like covering out more and more space. And what we can see, if I have this oriented right, I think, yeah, I think I want to flip this thing around. I did practice this earlier, I really did, is we can actually see what they call the Sloan wall. And nope, that's not it. Yeah, but basically it's some of those yellow chunks where you're getting like the denser regions. Yeah, actually I'm pretty sure that is it over here. This bit along here. So all along in here, that's this huge like conglomeration of several clusters of galaxies all kind of strung together. And the whole thing is about 1 billion light years from Earth. So if I come in, I measure out, yeah, that's the right speed. That's the one. So it's that string along here, all connecting this group and all these groups in orange, these denser regions. So they call it a wall. I mean, obviously it's not like a physical wall there, but that's one of the largest structures, so to speak, that we see in the universe. And then in between you see all those voids. So a lot of the walls, a lot of the huge like filaments that they call, like the strings and the kind of wall features, have names. A lot of the voids have names. If we move in a little bit closer, we can turn on, I think I wanted the 2 mass, and we can lose the 2DF. And then some of these actually do have, yeah, so we can start to see some of these regions where there's voids. And actually we'll just do the Tully set. So this is a Tully set of galaxies, just all different surveys. So Tully only has about 30,000 only, but you might be able to see some of these regions if we spin it. It's kind of like a cube shape, a cube-shaped data set, if you move out there. But you can see like definitely the oranger areas, those are denser. And then you can see how they're almost like strung together where there's dark matter basically connecting them. So they're kind of clumping around these dark matter filaments and forming more matter all around them. And then the spaces between, we have these voids. So if I kind of flash the galaxies off and on, you can see where some of those emptier bits are, all the voids between the galaxies. So lots of stuff in space and then lots of space between them. So a lot of the voids are going to be just as vast, just as long as some of these huge clusters. And as we come in here, we can start to see, let me see if we have the supercluster labels, galaxy cluster labels. So yeah, and here we have the Virgo cluster. So that's kind of the main cluster that we are part of. So we're not like in the center by any means. We're definitely out in the boonies. But you can see we're in kind of like this kind of filament, this larger scale structure with several clusters kind of all kind of grouped around us. And that doesn't make us special. That just happens to be where we are because we look around and we see these filaments, we see these groups of clusters in all different directions. So I just wanted to kind of leave us out here with like kind of a pretty view. If we turn off some of our labels and turn up one of the other images. And there was another question earlier about the moon making it difficult to see the Mini Dipper. Not so much if you have binoculars, it'll still show up. Even with the naked eye, you can still see the Pleiades cluster, and the moon just it'll kind of drown out the fainter stars. But a lot of the stars in the Pleiades they're pretty bright. They kind of stand out. So, so this is kind of an artificial view of our region of space. All the Tully galaxies, again, that 30,000 galaxies in this data set, but these are magnified. So the galaxies aren't actually this big, but you can kind of still see like some of the groupings. And where we are, like in our local group, it's relatively void. Like if we kind of zoom in and see like, oh, this is us over here, like this little grouping in here, but these are all, again, magnified. So the Milky Way and Andromeda and Triangulum. So it's just kind of like the 3 large galaxies and a few small galaxies together. But if we were out in like one of these clusters, like in the Virgo cluster, I'm not sure if this is the Virgo cluster up here, but goodness, that is a huge cluster. How different our night sky would be. And like having a lot more galaxies that would be visible to the naked eye, assuming that we don't have bright moons and other things kind of drowning them out. So it wouldn't look like this. This is artificial, but it's just like one of my favorite like fake scenes to recreate, and just think about like where we are in the universe and kind of our perspective and our view compared to some of these other not too terribly far away. So again, that Virgo supercluster, that's kind of our downtown that we're still part of. But we're out kind of in the boonies. And I just turn that off in our home galaxy. So I'll just kind of leave us here out with a nice little view of our galaxy top down. But yeah, if you get a chance to see it, probably not going to see the Milky Way galaxy in the sky this week with the moon so bright coming like kind of right past it. But check out those 2 clusters, the Pleiades and the Hyades. Again, really nice to see. Either just naked eye, try to pick them out, or if you have binoculars, you can see some of the bright stars in there. So thanks so much for tuning in. Hope you got something out of it, and I'll tune in again next week. Again, I'm Irene Pease, your friendly neighborhood astronomer. The visuals I've been using are Stellarium, which you can find at stellarium.org, and OpenSpace, which you can find at openspaceproject.com. Thanks for everyone for joining us for this tour around our celestial neighborhood. Be safe out there, clear skies, and wear a mask.